Now we're going to be doing section 4.1, and a lot of what you're going to see in this first part of chapter 4, which is on trigonometric function, will be a review from what you did last year and a little bit of review from what you did in geometry. But mostly what you've dealt with so far is doing trigonometric ratios when you're dealing with degrees as your angle measures. And so what we're going to start using now is a measurement called radians. And so in the diagram below, theta is the central angle of arc A in a circle with a radius of h. If theta were 30 degrees, we would say A is a 30-degree arc, just like our central angles were in geometry. It's useful to be able to measure A in the same units as the other lengths in the picture. This led to measuring theta using a linear unit called radians. So a central angle of a circle has a measure of 1 radian if it intercepts the arc with the same length as the radius. So if I draw a radius r and another radius r, if this arc length is also r, then this arc length is considered to be 1 radian. So we're going to be doing a little experiment in class. And so if you're not doing this in class, you might pause it right now and do this experiment where you just draw a circle. We're going to be using compasses in class, but you could take any circle at home and trace it around. And cut a piece of string the same size as the radius of your circle. Place one side of the string at A and bend it around the circle counterclockwise, marking the point B on the circle where the other end of the string ends up. Draw a radius from O to B, and the measure of angle AOB is 1 radian. So if I start going around this circle, and obviously I'm estimating this, but I say this has the same length as the radius, then I'm going to mark that as B. And so AB, arc AB, is now 1 radian. And so we need to, what is the circumference of the circle in terms of its radius? Well, if I continue around this circle, what we'll find out is that if we're fairly accurate, we're going to come up G, oh, it's moving on me, F, G. We're going to find out that we come up slightly short as we're moving around with our radius. And so why are we slightly short? Because a circle, if you think about a circle, pi is a ratio of the circumference to the diameter. So as we took this radius around the circle, it'll fit 6 full times, but then we have a little bit of the circle left. So what is the circumference of a circle in terms of the radius? Circumference is 2 times pi times the radius. So how many radians must there be in a complete circle? Well, that would simply be 2 pi. Because to find the circumference of the circle, we multiply the radius times 2 pi. So the radius fits into a circle 2 pi times. So how many radians must there be in a complete circle? 2 pi. If we cut a piece of string 3 times as big as the radius, would it extend halfway around the circle? Why or why not? Well, it wouldn't, because 2 times pi is actually 6.28. And so if we take 3 radii and extend them around our circle, well, there's 1, there's 2, there's 3, we're going to find that we are just shy of being able to make that a complete semicircle. And that's because of the ratio of the circumference to the diameter when the mathematicians of yore came up with that ratio of pi. So how many radians are in a straight angle? Well, here is our straight angle, and if an entire circle has 2 pi radians, well then half of a circle, which gives us that straight angle, is going to have pi radians. So we're going to use this degree of radian conversion in just a second. To convert radians to degrees, you're going to multiply by 180 degrees divide it by pi, and that's going to give you the radians. To convert degrees to radians, you're going to multiply by pi over 180, and that's going to give you the radians. So find the degree and radian measure of each angle in the circle below. Well, we're going to start off at 0 degrees, and that's also going to be 0 radians. We're going to first figure out the easy ones. If we go over here, this is 180 degrees, but like we just said, in radians, this is pi. And I'm always going to write radians on the left, and I'm going to write degrees on the right. So we started off at 0, 0. Now let's look at 90 degrees. So up here at the top we have that that's 90 degrees, but if this whole semicircle is pi, then in radians, this angle up here is going to be pi over 2 radians. And now let's look at 45 degrees. So 45 degrees is halfway between 90 and 0. And so 45 degrees, we're going to say that that's pi over 2, and it's half of that. So this is actually going to be pi over 4. Now these are ones that are fairly easy to get using common sense, but let's start using our conversion factor that we talked about just a second ago. To convert radians to degrees, multiply by 180 over pi. To convert degrees to radians, multiply by pi over 180. We're going to use that second one because I think it's a little bit easier. Now this is our unit circle, and so what I'm going to do first is I'm going to go around and I'm going to start labeling all of the degrees that are our pretty degrees for our unit circle. So we have 30 degrees, and then we have 60 degrees. Remember, it's all the measurements that gave us our special right triangles. That's how we get these. And then we go to 90 degrees. 90 plus 30, we're at 120 degrees. And then we're at 135 degrees, 150 degrees. And then it makes the jump to 180. 180 plus 30 would put us at 210 degrees. And then we're at 225 degrees. And then 180 plus 60, that's 240 degrees. This is 270 degrees. This is, this is 300. This is 315 degrees. And this is 330 degrees. So those are our special degree measures as we go around our circle that would give us our special right triangles. So looking back, we're going to convert that to radians by multiplying by pi over 180. So if we multiply 30 by pi over 180, and we cancel out, we get that it is pi over 6. And we know that one is pi over 4. So over here we're going to multiply 60 times pi over 180, and we get pi over 3 radians. So over here we have 120 times pi over 180. Oops, it's moving on me. And if we simplify 120 over 180, that's going to give us 2 pi over 3. This isn't showing up awesomely. 135 degrees. So 135 times pi over 180. Well, I can divide both top and bottom by 45 degrees, and that's going to give us 3 pi over 4. 150 pi over 180 is divisible by 30, and that is going to give us 5 pi over 6. And 180 degrees, that's just pi. We've done that one. And so now here we have 210 pi over 180, and if we divide by 30 on top and bottom, we're going to get 7 pi over 6. Now, if you're doing this at home, pause it now and figure these out on your own. I should have said that at the beginning. So now we have 225 times pi over 180, and that'll be divisible by 45. So that's going to give us 5 pi over 4. 240 over 180 is going to give us 4 pi over 3. And 270 over 180 is going to give us 3 pi over 2. And going to 300 over 180, divide by 60 on top and bottom, and that's going to give us 5 pi over 3 radians. 315 over 180, that's divisible by 45, and so that's going to give us 7 pi over 4. And then 330 over 180, that's divisible by 30, and that's going to give us 11 pi over 6. And then now we're back to our beginning, and so we can say that it's 0 radians, or once we've gone all the way around the circle, we can say that it's 2 pi radians. So convert the following from radians to degrees. Well, when we're converting from radians to degrees, we're taking pi over 10 times 180 over pi. And whenever we're converting from radians to degrees, these 2 pi's will always cancel out. So we end up with 180 over 10, and that's going to be 18 degrees. So now we have 13 pi over 20. We're going to multiply by 180 over pi. Pi's cancel out. 180 divided by 20 is 9, and so we end up with 13 times 9, which is 162 degrees. Now we just have 2, so we're simply going to take 2 times 180 over pi, and that's going to give us 360 over pi degrees. And if we're multiplying 1 and we're converting from radians to degrees, we're going to just take 1 times 180 over pi, and that's just 180 over pi degrees. Now I would change those into decimals since we are dealing with degrees, so I'm actually going to do that on my calculator now. So 360 divided by pi, that gives us 114.59 degrees, and 180 divided by pi gives us 57.296 degrees. And I probably should have rounded to thousandths place, because in a couple of minutes we're going to talk about how to take these degree measures and convert them to minutes and seconds to be more accurate in the degree measure. So convert the following from degrees to radians. So this is where we multiply times pi over 180. So we're going to take 60 times pi over 180, and that's just going to give us pi over 3 radians. And 90 times pi over 180 is going to give us pi over 2 radians. 120 times pi over 180 divide by 60, we're going to get 2 pi over 3 radians. 180 times pi over 180, that's just going to give us pi. So there's our semicircle. And 150 degrees times pi over 180, divide by 30 on top and bottom, and we get that it's 5 pi over 6 radians. So now find the radian measure of a central angle that intercepts an arc length S in a circle of radius r. So arc length formula for radian measure: if theta is a central angle in a circle of radius r, and if theta is measured in radians, then the length S of the intercepted arc is given by S equals the radius times theta. And so these are pretty straightforward. It's just going to be hard to differentiate between this formula and the next one. They're a little bit difficult to remember because it's easy to get the pieces and parts mixed up. So we just have the arc length equals the radius times theta. And in this problem, we have that the radius is 9.9 and theta is measured in radians. So we're going to take 9.9 times 4.8. And we get that it is 47.52. And that's in feet. And here we have that the radius is 4.1 kilometers and theta is equal to 9.7 radians. So we're just going to take S equals the radius times theta. So 4.1 times 9.7 is 39.77 kilometers. But what if we're given a degree measure of an angle? In this case, we're going to say S equals pi times the radius times theta over 180. So we're actually including that conversion measurement within the formula when we're going from degrees to radians. And so for this one, we're given that the radius is 40 centimeters and theta is equal to 20 degrees. So we're not in radians. So we're going to say that this is pi times the radius times theta all over 180. And when I look at what I can cancel out here, I know that I can cancel a 0. And now we have pi 80 pi over 18, so I'm going to divide by 2 on top and bottom, and so this would be 40 pi over 9. Now when we're actually talking about an arc length, we should change that into a decimal. So we're going to say 4, this is exact, but it doesn't make a whole lot of sense to use it because it wouldn't mean anything to anybody to tell them, oh yeah, that arc length is 40 pi over 9. So when I multiply that out, I get that it is actually 13.963 centimeters. And so for this one, we have a radius that's 3 inches, and we have theta is 130 degrees. So we're going to say S equals pi times the radius times 130 over 180, and I know I can cancel out those zeros. It's the same as dividing by 10, and I know I can cancel 3 over 18. That's going to be 1, and that's going to be 6, and so I end up with 13 pi over 6, and that's what I'm going to put in my calculator. 13 times pi divided by 6, and we get that this arc length is 6.807 inches. So angles in degrees and minutes and seconds. A degree is a unit of angular measure equal to 1/180th of a straight angle. In the degree-minute-second system of angle measure, each degree is subdivided into 60 minutes, and each minute is subdivided into 60 seconds. So convert the degrees, minutes, seconds into decimal form. So if I read this, this is 23 degrees and 12 minutes. That single little apostrophe up here means minutes. If we have 2 of them, then that's talking about seconds. So to change this into a decimal, we're actually going to say that this is 23 plus, there's 60 minutes in a degree, and so we're going to say plus 12 over 60, and 12 over 60 is actually 0.2, so this would be 23.2 degrees. Now for this one, we have 48 degrees, 30 minutes, and 36 seconds. And so what we just did, so we have 48 full degrees, and then we have 30 minutes, but how many seconds are there in a minute? Well, in this case, we actually have to say, okay, there's 60 seconds in a minute, and so there's 3,600 seconds in a degree. So we're going to say this is plus 36 over 3,600. And when I convert these to decimals, we have 48 plus 0.5, and then 36 divided by 3,600 is 1/100th, and so this would give us 48.51 degrees. Now, if we're converting a decimal form to decimal minutes and seconds, well, in this case, we're going to have 21 degrees, but then we need to multiply 0.2 times 60 to figure out how many minutes that is. So when I do 0.2 times 60, I get that it'd be 21 degrees and 12 minutes. And there was no remainder from that. So now on this next one, we have 118 and 32 hundredths of a degree. So we're going to do 118 degrees. Now I'm going to do 0.32 times 60. So 0.32 times 60, I just did divided. 0.32 times 60 gives us 19.2. So we're going to take those full minutes and say 19 minutes. Now I still have this 0.2 decimal. So I'm actually going to take that 0.2, because that's 0.2 of a minute, and multiply that by 60 to figure out how many seconds that is. So 0.2 times 60 gives us 12 seconds. So we have 118 degrees, 19 minutes, and 12 seconds. Okay, a bearing is the angle of the line of travel measured clockwise from due north, and this is something that sailors use a lot. So find the angle in degrees that describes the compass bearing. Well, when you think about a compass, you have pure north, and you have pure south, and you have pure west, and you have pure east. From there, exactly halfway in between north and east is going to be northeast, and exactly halfway in between south and east is southeast, and halfway in between south and west is southwest, and exactly halfway in between north and west is northwest. But then we can break it down a little bit further, and let's say we have this in here, and it's more north than west. This is called north, northwest. And then we have this angle in here, and that's more west than north, so this is actually called west northwest. And then this one here, that's more west than south, is called west southwest. And this one here is called south southwest. And this one here is called south southeast, because it's more south than east. And this one here is called east southeast. And this here is called east northeast. And the last one here is called north northeast. So when we think about how many sectors we just divided our circle into, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we just divided 360 degrees up into 16 regions. So each one of those is 22.5 degrees. Now, whenever you're figuring out your bearings, you're always starting at 0 degrees is considered to be north. And from that northern measurement, we're actually going clockwise, and so we're measuring it in a direction going around this way. So south-southwest is all the way around, so it's past 180 degrees, and then we went another 22.5 degrees. So if I'm looking at south-southwest, there's 180 degrees, and then we have another sector that had 22.5 degrees. So southwest is 202.5 degrees. Now west northwest is almost all the way up to the, well, no, it's just right over here. And so for west northwest, I'm going to go all the way around to here because I know that that's 270 degrees where the green is. And then I know that it's another 22.5 degrees. And so that's going to be 292.5 degrees. And north-northwest, well, if this is 0 or 360, I know it's just shy of going full circle. So for this one, I'm going to say that it's 360 minus 22.5. And that gives me 337.5 degrees. And so that's it for this section. The homework for this section is the 9 math Excel problems that are online, and that is it, because I'm hoping that you can have a math-free Thanksgiving break. Have a good one.